Hi everyone. Today I'll be presenting you on the peridynamic modeling of propagation of cracks in photovoltaic panels. My name is Andrew Johnson Premchander. I'm a PhD student and research assistant at the University of Strathclyde, Glasgow, UK. My co-authors are Dr. Islam Amin, Dr. Selda Oterkus, Dr. Erkan Oterkus, and Dr. Nabil Ahmed Shawky, Elminshawy. My presentation outline consists of a short introduction about photovoltaics and a short introduction about peridynamics, numerical modeling of crack propagation, discussion on the results, and conclusion. Photovoltaics, commonly known as solar panel. To reduce carbon emission and local air pollution, the world is rapidly shifting towards renewable energy. Today, solar energy is widely used in many aspects, from residential properties to international space stations to rovers on Mars, and even on household items such as phone chargers, motion sensor lights, and many more. They are not only used to power single equipments. There are mega solar farms and offshore floating systems around the world in many locations which can power a full city. This dependency and renewable source of energy from sunlight brings us to the importance of this research. There are three most commonly used solar panels that are thin film solar panel, flexible and portable, monocrystalline solar cell, from the look is black in color with chamfered corner. It is made out of single silicon ingot. Polycrystalline solar cell, from the look it's blue in color with the square edges. They are made out of many fragments of silicon fused together or melt and joined together. Each one has its own advantage and disadvantage, but our concentration is on the polycrystalline solar panel as they are widely used in many mega projects. Advantages are the manufacturing cost is cheaper and more eco-friendly. The drawbacks are the cell efficiency is only 12 to 14% and the lifespan is between 20 to 25 years. If you look deep into the working principle of the solar panel, the main ingredient of the solar panel is the silicon that acts as semiconductor, which helps in transferring the electron from N-type to P-type semiconductor, producing an electric current. Since the efficiency of the solar cell is dependent on the active cell region, it is equally important to understand the crack growth that causes the inactive zones. There are several causes. It may be even because of expansion and contraction of the silicon itself, or even during the manufacturing process. Let's try to find out how the crack propagates in polycrystalline silicon panel using peridynamics. Before jumping into simulation, a brief introduction about peridynamics. Peridynamics is a new continuum mechanics. In continuum mechanics, material are considered as continuous mass rather than a discrete particle, and the governing equation is a partial differential equation. But the equation fails when there is a crack or discontinuity. For ages to overcome this limitation, various studies on fracture mechanics have improved to identify the different characteristics of the crack. Still, there are limitations when multiple cracks that propagates in a complex manner. That's where the peridynamic formulation comes into effect. Peridynamic uses the integral differential equation, where the discontinuity is incorporated into the equation. Therefore, the equation continues even if there is a crack. This type of numerical modeling works even if there is a multiple crack. The major types of peridynamic modeling are ordinary state-based, non-ordinary state-based, and bond-based peridynamic model. In this experiment, I have used bond-based peridynamic model. Bond-based peridynamic has equal magnitude in directions to each other. To understand the concept, let's consider a plate with predefined length and width. The material properties are defined by density, elastic modulus, and Poisson's ratio. In peridynamics, the plate is divided into several material points without mesh. Each material point defines a mechanical property of the material character, and each point is interacting within the neighboring material points within the horizon delta. The interaction between 2 points is called the bond. So when a plate is subjected to a tensile load, the bond between the 2 points stretches and the bond breaks beyond the critical value. The critical stretch value is a function of shear modulus, bulk modulus, and critical energy release rate of the material. Now let's consider a polycrystalline silicon of dimension 5 mm by 5 mm with two cracks of 0.4 mm on left and right edges. Is subjected to a tensile load of 25 meter per second velocity at top and bottom. Here two grain boundary coefficients are considered. First condition where the grain boundary is 0.5, meaning the bond strength of the grain boundary is weaker than the grain itself. In second condition, grain boundary is assigned to be 2.0, that is the grain boundary strength is twice the grains. The following simulations are the results of the bond-based peridynamic code were modified from the original code to suit the current requirement and prepared for crack in silicon by myself, and the animation video were prepared by Blender. Case 1. Let's see how the crack propagates without considering the microstructures. From observation, the crack is in straight line. In most of our finite element analysis, we don't consider the microstructures, and the result is a straight line. The next simulation shows the importance of considering the microstructures during the finite element analysis. In case 2, the same polycrystalline silicon plate is modeled with microstructures. At microscopic level, the grains are formed during crystallization of solid when there is an uneven growth. The grain boundaries are defined as the contact region between the grains. Here in this simulation, the microstructures are considered with grain size ranging from 0.33 mm and the grain boundary coefficient is 0.5 times. That is, the grain boundary bond are weaker than the grain itself. Let's see how the plate reacts in time. From this observation, the crack propagates through the grain boundary. This proves the importance of considering the microstructures. There is one more case, case 3, with the grain boundary coefficient is 2.0. This is a simulation where the grain boundary coefficient is twice the grains. This happens when the impurities are trapped within the grain boundary, which constitutes the strength of the bond. Let's see how the plate reacts in time. From our observation, it is similar to case 1 but deviates when the crack meets each other. A comparative study was done to understand the crack propagation behavior with difference in grain size. By keeping the horizon diameter constant to 100 micrometer, variations of grain sizes were compared. Here 9 simulations were done with 3 grain boundary coefficient, and you can observe how the crack propagates different in each cases. And another study was done to understand the impact due to horizon diameter by keeping the grain size constant. In here, by changing the horizon diameter indirectly increases the number of material points within the region. Therefore, as the number of material points increases, the accuracy of the crack growth increases. Therefore, in conclusion, the importance of identifying the crack growth in polycrystalline photovoltaics will be helpful to identify the inactive zones causing the reduction of solar cell efficiency. The accuracy of the crack growth and percentage of inactive zones will be helpful to decide the lifespan of the solar panel. This research proves the importance of considering the microstructures to investigate any polycrystalline material. And these are my reference, and thank you for listening. I hope this video will be helpful. See you again in a new topic. Bye.